Hi, and welcome back to this book club on the space economy. And this one actually is going to focus a lot on this interstellar travel book. And this is the propulsion section. Right? So a lot of this, whether you're talking about opening up the near-Earth stuff, so like moons and asteroids, or if you want to expand that to Mars, you expand it to the solar system. In this book, eventually we'll talk about expanding to other solar systems. This is a good technological overview of the problems. We have a problem with propulsion. Okay, and we'll kind of get into the problems with like the medical sciences and things like that along the way too. But those are kind of the two broad categories of how this is hard. First, getting around, and the second one is keeping humans alive, if you will. Okay, and so from a propulsion point of view, just a little bit of a reminder, and I've done this in other book clubs, and you can look at even some of the Venus high-speed flight stuff, but just to start off a little bit with propulsion. And so if you have F equals ma, right, that's your normal formula, but the force coming out of a rocket engine, so if I were to draw a rocket engine, basically you have oxygen and fuel coming in, and you mix it, and so this gets really hot and high pressure. So I'll just say high pressure. And then through a nozzle you exhaust at some really high speed. You basically convert chemical energy to thermal energy to kinetic energy, to thrust. Okay? And so the force on this is actually the mass flow rate of the engine times the velocity of the exhaust, and that's equal to mass and times acceleration. Although again, I'll switch this to dv dt. Okay, and so then you can put velocity on this side. So this is now dv dt is equal to, and then the mass of the engine is actually the negative m dot of the rocket times, and I'll put ISP times g. That's normally how we define the exit velocity is ISP times g. And I'm not accounting for any pressure adjustments. This is just the basic formula. And so then this m got divided by down here. And so that's where you end up getting a natural log. And so what we then say is delta v is equal to ISP g, and then you get a natural log, and I usually have it in this form. That's the way I write it, where lambda is the mass, that's the total mass of your propellant divided by the total mass of takeoff weight. Okay, and so that's the normal thing. So usually, ISP is a big deal. But if you've seen some of my other book club stuff, really this is just sort of the engine efficiency side of things. You actually have to look at the whole system as well. And so you could have systems with great ISP, but the mass of the engine is incredible and it doesn't pay off. So while this performance is important, you really got to pay attention to it at the highest speed. Okay, and so the way I usually calculate that, and we'll see if I can switch to a slightly different color on that one. Basically, that problem, you say I have some vehicle that is really a different color, and that vehicle is made up of some systems. Okay, it's made up of some structure. It's made up of some payload. That's the thing you're trying to carry. It's made up of engines, and then it's made up of propellant. Okay, so you divide by m through this whole thing, you get 1. And then the way, and this actually, you can go look at the Kucherman series where I did this. Usually what you end up saying C1, which is some combination of systems and structures at the sort of vehicle level. And then you have P is a fraction of payload, 1 plus C2. And the C2 is sort of how much weight, relative weight it takes to hold the payload. That way, the payload can be humans if you want, or it could be satellites. And the C2 would be like everything to keep the humans alive and secure the humans or secure the satellites, all that. The engine, this one you can actually say is a thrust weight of the vehicle divided by thrust weight of the engine. Okay, that gives you the mass, and then same sort of thing. 1 plus C3. This is how much it takes to hold the engines. It's not 0. And then you have lambda, I already defined that as above, and then it's 1 plus C4. And this is, again, how much it takes to hold that propellant. Now you got to be careful because the amount of structure it takes to hold, say, like liquid hydrogen, this could actually eat your lunch pretty good, versus dense propellants like liquid oxygen or hydrogen peroxide and things like that. So this is a system equation you got to pay attention to as well. In addition, so we have sort of the performance equation, but this is the total systems engineering thing. Okay. And then what interstellar travel we'll get into. So what is a little bit different? Last time I sort of showed you the ISP plot of going around to all the different planets. And so, yeah, it's some combination of this. You can think of sometimes as what we seem to really need to do is chemical propulsion on the way up, and then you can switch to electric propulsion if you want. But one thing I want to cover is gravity assist. Okay, gravity assist. And what's happening there? So imagine you have some sort of planet, and from the planet's point of view, here comes your satellite or your probe or your vehicle, and it sort of, just bends around. Okay, well, that's from the planet's point of view. What's actually happening, though, is the planet is starting here, and I'm going to exaggerate, and it's going to move to here because it's orbiting the sun. And so as I start this, ultimately, you can see I'm actually getting drug along. And so I actually get this kick. I get a plus delta V kick if I do it that way. Likewise, there's actually a braking maneuver. So again, if your planet starts here and goes here, and you sort of bring your satellite this way, you'll have a braking maneuver. Okay, so that'll be important on if we're doing sample returns and things like that. Okay, but this is a boost maneuver. Okay, and so actually, the calculations can get really, really complicated. There are some pretty easy ones, but what I would say is Brain Shuffle has made a really great video series here. Go look on the YouTube where they talk about all the complexity of trying to track all these probabilities. And because it's one thing to just do it a couple different times or do it as a coasting maneuver, right? As soon as you say, well, I can fire my engine at any given point, it actually quickly turns into this probabilistic map with manifolds and weak stability, and it's called the Interplanetary Transport Network. So there's actually been a lot of research going into this because it is pretty computationally intense, and we're actually starting to see some really interesting pathways through our solar system that can give us these sort of lower energy trajectories as opposed to just, I showed you the kind of the pork chop plot last time. So that was pretty interesting. And then kind of final step here that the book does kind of talk about, but it's important to know, is actually the Lagrange points. Okay, and so what I'll draw here is, honestly, any two-body system is going to have this. So you can say this is Earth, or you could say it's the sun. Okay, and then let's say out here I have the moon. Again, this could be Sun and Jupiter, whatever you want to do. There's a couple Lagrange points, and so here's Lagrange point 1. And what this means, this one's the easiest to understand, is that this is the point where if you put something there, it feels the same amount of pull towards Earth as it does towards the moon. Okay. Now, on some of these Lagrange points, there's stability, and other times there's not. So this one's actually unstable. As soon as you creep a little bit further towards the moon, you're going to get pulled towards the moon. Okay. But remember, the moon is actually orbiting this way the whole time. And so, in fact, this L1 is also moving and orbiting. Okay? And so you then also have, because of all of this, you have L2, which is also a stable point. Basically, both the Earth and the Moon are pulling, whatever you're placing at L2, both Earth and Moon are pulling at it, right? But it's stable, and it's kind of orbiting around. So that was pretty cool. Okay, in fact, this is where we're putting the James Webb Space Telescope. And we're doing it such that it is basically hidden. It is the Sun-Earth. So the James Webb Telescope is at the Sun-Earth L2, such that it is always in the shadow of the Earth. So this would be Sun, Earth, and then L2. All right, that's pretty cool. So fun stuff. There's one over here as well called L3. And then you have sort of behind the thing, kind of trailing the moon is L5, and leading the moon is L4. And those ones, like in Jupiter asteroids, are called the Trojans. In fact, this one I had to write down. These ones are actually the Trojans, and these are the Greeks. So there's actually a set of asteroids there in each one of these spots, and about 60 degrees in front and behind. So some stable points. Okay. Now, while L1, L2, and L3 are not necessarily stable, there are actually some interesting stable halo orbits that kind of go around these things. And so as long as you're sort of, you can almost orbit those points and they're stable. So kind of popping into a third dimension. So there's some really, really cool stuff there. I think I've got, no, I don't have the L3. No, I didn't put the halo orbits as a picture. Okay. So those are kind of your basic, dynamics and, gravity assist, as well as places where you might want to put things. Oh gosh, I didn't realize L3 is off the screen. Okay, I'll put it here, L3. All right, I'll have to fix all this for next time. But now I want to talk through then propulsion systems, okay? And that's kind of what this curve is about. This is specific impulse versus thrust. And so you end up seeing, if you want high thrust, you got to be sitting down with chemical. That's basically the only way to do it. Nuclear thermal is coming along. It will have some high thrust, but it doesn't have a massive jump in ISP compared to chemical. So there's actually some fields of people saying, like, it's not a big deal. In fact, I've seen some initial analysis that say nuclear thermal only like doubles your payload. And it's like, boy, that's for all the pain to get approvals and all of the challenge of nuclear, only getting double the payload is kind of crazy, right? That means like you do all that work for double the payload as opposed to just sending 2 rockets. So it's not a massive jump. We'll kind of talk through some of the other ones, and then electrothermal, electrostatic, electromagnetic. There are some other ones here that whether you have sort of solar power to collect the energy and do it, they have much higher impulse, but the thrust is low. So these are okay. Like once you're out of the Earth's atmosphere, these are okay for station keeping. Some of these can be okay if you sort of use your chemical rockets to kick towards, kind of get your escape velocity from the Earth, and then you can turn these on to kind of keep pushing. It can be sort of helpful. So let's talk about the big broad categories, okay? And so the first broad category is fission. And then we'll come back, we'll talk about fusion. And then up here, to give myself a little bit more room, I'm going to talk about antimatter. Right, and these are kind of getting more and more advanced. And then I'm going to talk about then reactionless as well. So things that you don't have to carry. All right. So from a nuclear fission point of view, and it's pointed out of this book, really there's nuclear thermal. Already mentioned that a little bit. I think I have a picture here of a nuclear light bulb. Okay, and so this one is one of the versions where you have sort of a, I don't think this is quite a liquid core. Do I have the liquid core one here? Not yet. Fission fragment. Okay, okay. Where basically you're heating up, you're always heating up some sort of reaction fluid. Okay, you have nuclear electric, where you just basically have a nuclear power system on board, and then you're driving an electric thruster. So this is sort of gets you back to, if your solar power is limited, come back here. It'll let you do sort of one of these electrostatic or electromagnetics, but powered by a nuclear system. So hopefully that pushes it towards, a little bit sort of medium thrust levels. Okay. You have the liquid core, and some of these are interesting where you're kind of centrifugally stabilizing. You end up having some amount of leakage of radiative stuff out the back. So this is one of those things that's not able to be tested here on Earth, really, but you could send it out in space, and I don't think we're too worried about sending radioactive material out in space. Space is already full of tons of radiation. And so this has got an interesting promise. It's just a matter of getting it tested would require doing this in orbit. But hey, that's one of the point of this talk. This is actually, so I'm going to sort of highlight this one. Maybe this will come through. Highlight this one in red. No, that didn't come through. Where's my orange? Highlight this one here. There we go. This is one that, as launch cost comes down, we might be able to actually test in space and really show the power of it. Okay. You have a gas core, which is a little bit of the same thing. Kind of switching materials and kind of gaseous, you get some exhaust. And then fragments. So this is the picture I have here. This is from NASA SAIC study. So what's happening with fission fragments is you're actually like letting the uranium split, and some of these fragments of the result of splitting uranium you actually send out at high velocity because they already have high velocity. So as opposed to slowing them down, thermalizing them to create water or whatever to create heat, then push hydrogen or push water, you just sort of let it out the back. And so some pretty high ISP, but very high on the radiation scale. So again, this one I'll highlight as, hey, these have high potentials, but they have to be done in testing in space. There's almost no way we can do sort of ground-based testing on these things. And then the last one I'll mention here is pulsed. Okay, there's a lot of pulsed nuclear reactors, especially in academic universities. So pulse is a way where you can get the total energy of the system to spike like crazy and then thermally shut down. And then you can bring it back up and spike like crazy and thermally shut down. So you actually get, on average, a higher usefulness out of the uranium. So normally the nuclear reactors we have, once they go critical, we keep them kind of barely critical. If you ever heard of nuclear power plants, they'll brag about how they don't have to refuel for like 20 years or 30 years, or submarines doesn't have to refuel for 20, 30 years. They say that's a pro, and the answer is like, well, if you're a submarine, you're gonna have to come back and port to get more food for the humans and things like that. It's actually, it's just that we don't really utilize the nuclear power quickly. So pulse is actually a way to sort of get into a pulse operation where we are actually increasing the burnup, which ultimately brings the size of the engine down. So back to this sort of here, it actually, the thrust, the weight of the engine, it gets the size of the engine down, has a massive effect. And so where your ISP, your ISP is important for how much propellant you need to carry, pulse power would actually really help this term here from thrust to weight. So that's a great option. Okay, fusion. Here's a picture of a fusion direct drive. And so, if you can get nuclear fusion, we always seem to be, decades away from fusion, but if you can get fusion going, then you just really kind of power the exhaust at the back. And so there's a couple different fusions. There's magnetic confinement. There is the direct drive here that you see, magnetic confinement plus direct drive. There's one called the Bussard ramjet. And this is where you actually have a big, massive magnet trying to, grab helium or grab hydrogen in front of you, and then feed it into the engine. The size of the magnetic fields here to actually scoop up all that hydrogen is pretty crazy. So this is high on the kind of crazy list, or low on the TRL, if you will, but it's sort of interesting. And then what's right here? Yeah, give me some black space. You have inertial confinement fusion. This is where you hit it with lasers. You have little pellets that you make, you hit it with lasers. So we're getting some good progress there. And then magnetic fusion, so kind of pulsed magnet. I did some work on this as an undergrad, actually, in dense plasma focus. So, I've always thought this would be one of the ways to go. So that's pretty good. And then I'll finish here with antimatter. So antimatter is where you take say, like an electron and a positron, or maybe you're taking a proton and an antiproton, and you basically, they completely annihilate and release a ton of energy. Now, the energy that's released is actually normally in the form of radiation, so high X-rays or even gamma rays. So sometimes actually capturing that and turning into heat can be challenging, okay? But the nice thing about the proton and antiproton reaction is you actually get, for a little while, you actually get some pions, okay? And you can at least direct some of those pions out the back, so kind of, using some magnetic fields to direct them, and then when they radiate out into radiation, it's a little bit better. So this one has some imaging potential. Of course, we really can't make a ton of antimatter very much, and also, also holding the antimatter, kind of containing the antimatter is actually one of the biggest challenges. Okay, and then there's sort of a blending of the two. So there's a blending here where you have antimatter catalyzed fusion, where you use it to help sort of achieve the temperatures that you need for fusion. So pretty interesting. Okay, and I want to highlight a couple different things. Some challenges, and then I'll sort of finish up with reactionless stuff. So right here in the middle, Okay, challenges. Okay, challenges. All of these require reaction mass. This is water. Honestly, that water is going to be a thing. That's why in the previous episode I was talking about the moon being the source of water. It's actually going to be the source of propellant. So whether you're splitting it into hydrogen and oxygen to use in a chemical reactor, like for a rocket engine, or you're just having the water to then, for the fission system or the fusion system to boil and send out the back, reaction mass is how you make thrust. And so there's going to be a big economy to either get water from the moon or get water from the rings of Saturn to provide for all the propulsion for all of these ships that are going to be buzzing around in this space economy. So reaction mass is a big one. Okay. The other one here is radiators. So all of these systems, like all of these thermodynamic systems, you can go back and look at some of the thermodynamic stuff I did on the kind of earlier book club. All of these thermodynamic systems, if you're heating the water and then you're expanding the water and shooting it out, or whether it's just, driving a fission loop, all of these require cooling. And where do you cool? Well, you're going to have to take, whether it's water cooled or ammonia cooled, you got to get it out to some radiators and then radiate it into space. And so the mass associated here with radiators is non-trivial. Back to this equation over here, that would be your mass of your systems. So that would be buried sort of in C1. The amount of radiation required to support that, or maybe it's over here and it's buried sort of within your engine system. The amount of weight to support the radiators is a big deal. So there's a couple challenges, right? So opportunities for people who can really innovate on radiators would be a really big deal. Okay. Finish with some reactionless stuff. Okay. There are solar sails. The solar wind, right? The sun is always pushing solar wind. And so we've done a couple of these experiments, kind of big, really thin solar sails, and it can kind of push you away. So super interesting. Probably more useful for probes. I don't know how, they don't provide a ton of thrust, and so it'll be really for small systems, but it requires no propellant, so that's pretty good. So this term sort of goes away, and it would be the thrust of weight here. Power beaming. This is where what you have on the system is sort of a receiver, and you're like blasting lasers at it. So all the power is sort of based on the ground. You're sending the power then through lasers to the system to catch it, and then usually drive an electric thruster. So that would be useful. And then the last one here I'll add is the quantum vacuum. Okay. Well, one of the interesting things we're seeing, in fact, I got a friend, Sonia Casimir, who's working on some of the stuff. We actually are seeing some interesting things in the quantum vacuum, that there's structure to it. So both that we can potentially get power from the quantum vacuum. If you ever watched like Stargate SG-1, this is the kind of 0-point energy type of a system. But there's also the second part of it, which is if there's structure to the vacuum, that means potentially we can actually hold on to it. And so maybe not having to push just reaction mass out the back. Maybe it's possible if we get some of the stuff right, we can actually push on the fabric of space through sort of grabbing onto the quantum vacuum, if you will. So, some pretty interesting research out there. I always kind of come back to that analogy of Shackleton going to Antarctica and, having a horrible time, dying, like year-long expeditions, and then literally 10 years later, we're flying airplanes over it, and we have boats, and we're skidoos and all this stuff. So, like, it's things that are, like, impossible. All of a sudden, some sort of technology insertion just is like, changes the world, okay, in terms of exploration and access to economies, okay? And so what I'd say, I'm going to fish here. If you want to watch a really good video on this, Limitless Space, that does a great job. Sonny White used to run it. I'm good friends with him here in Houston. But go watch this go incredibly fast. It'll motivate you. It'll talk through all of the stuff. And they are a nonprofit. They actually support some of this really advanced, concepts. I didn't get into things like warp drive and all that kind of stuff, but I'll kind of save that for maybe a future episode. So this is propulsion. So when you're thinking about near Earth economy, right now the best thing we have is chemical, and then you have sort of electric systems to kind of push around. So, getting to Mars, most of the studies say it would be a chemical rocket with sort of an electric push or a nuclear electric engine. Of course, SpaceX is trying to basically get into orbit and then refuel their system and then push again to Mars. Just because that 9-month transit to and from Mars is pretty brutal. And we'll actually get into why. So the next episode is going to be on the human side of things. So we'll get there. So anyways, this is the portion on space economy, how it relates to how are we actually going to go get around and get those asteroids or mine the moon or whatever we're going to do. So we'll see you next time. Thanks.